Welcome back. In this lesson we'll be discussing various optimization techniques related to lighting and illumination. It's an important topic to consider because lighting takes a very important role in delivering realism and making your scene look interesting. It adds atmosphere, but also, unfortunately, lighting does take a lot of performance hit. And if you're not careful with it, very quickly you might find out that your well-illuminated scene might be slowing down your game substantially on various devices of your end users who are using mobile phones and perhaps weaker mobile phones or maybe mid-range devices. So if they're not able to run your game smoothly, they'll not play it. And therefore you must make sure that you can support as many devices as possible to maximize your possible revenue and to increase the number of players who are playing your game. Lighting is a sure thing to help you with that. Just a few quick words before we begin. I want to go over the setup that we currently have. It's Unity 2022, and the scene that we're using is a free one. You can grab it from Unity Asset Store just by searching here for the Viking Village Universal Render Pipeline and finding it and adding to your assets and then clicking Open in Unity, or coming back into Unity, going into Window, Package Manager, let it load, make sure that you are on My Assets. Give it some time to refresh. And if it doesn't show all of them, just click Load All, so that all of the packages that you have are being shown. And perhaps click Refresh if it's lagging a bit. Here it is. You can download it and then import it. If it asks you to import extra dependencies, such as things for the URP, then just click Confirm and go along. Import it and place it in your project. Another important thing that you should include in your project is the _GM folder. This is a typical convention to have a folder that has underscore so that it sits on top of all other folders in this list, and has some very short name so that it doesn't contribute too much to the path of each file that sits in it. _GM is a folder where all of the project files will be contained and everything directly related into your game, all of your scripts, all of your assets will go into. And any kind of additional assets or additional tools that you might pull from the asset store, tools that can constantly change and be updated by their own developers, they will naturally be imported into the assets folder next to your _GM folder without cluttering your own structure. So you always know that inside of the GM, _GM, is everything that you and only you can put. All the other assets will end up elsewhere nearby of it. And finally, let's also make sure that we are using the same UV layout. I'll use the one that's more common for me. So I'll go into the top right corner and we'll save the current layout. But before I do so, I'm gonna grab each window and position it in the way that I like the most. So I like to have console on the right over here, and I like to have two project folders. So I'll right click on the project tab and go into Add Tab, Project, and drag it to the side. This way I can work with two different windows and I can open one folder and drag it from one place to another without having to try to squeeze it in one single window. And also the hierarchy should be on the very left so that it's very long, and inspector right next to it. This way, as I'm selecting something in the hierarchy, I don't have to, teleport and look at the right portion of my screen. I just select it here and then it's immediately right under my mouse. Because this lesson is going to be revolving around lighting, I'm going to collapse everything inside of the Viking Village scene, and we'll show you several things related to light optimizations. By the way, this scene is located in one of the folders for the Viking Village folder in the scene, the Viking Village. Double click it and it will open and position you somewhere around here. Coming back to the lights, there are several lights that Unity is using, and each one has its own benefits but also might be adding extra cost to your game. You should be responsible and recognize which kind of constraints each light imposes to you and what it means to add an additional light. So currently this scene, it looks pretty good, and it's being illuminated mostly by one single main light, which is the directional light. It's located in here in hierarchy. We can click it, right click in the scene view and press F to focus on it. And as I orbit around it, you can see that it's right on top of here. So the way that the directional light is working, and basically any kind of light in Unity game engine is working, is it is an entity which is sort of like a camera. And it's rendering the scene from a specific angle, for example from this direction, in an orthographic mode. And by doing so, it is able to recognize which sort of elements in the screen it is able to illuminate. Because anything that the light sees naturally is going to be illuminated and will have brighter colors. Anything that the light doesn't see, but anything within its range, is going to be covered in the shadow and is not going to be lit by this light. So the directional light that I've selected currently might see the scene somewhere from this angle, in an orthographic or isometric mode, not in perspective. And to show you this, I'm just gonna left click in the center of this cube to make myself go into the isometric mode and reorient the scene to maybe this angle. So this is exactly how the light would see it. And notice that anything that's covered and is not directly seen by the light is naturally going to be in the shadow. By doing this kind of rendering, light is creating a so-called shadow map texture. It's a single frame that the light is observing at any given moment in time, and it might look like something like this. So for the light, it doesn't really care about the colors of objects. What it cares about is how far each fragment is away from this light source. If it's far away in the texture that the light sees, the pixel is going to have a whiter color or brighter color. And if the color is darker, this is a way to signal to the light that, hey, this part is very close to you. And this way the light is able to reconstruct depth of the scene by just looking at a two-dimensional image. So it's like a depth map, but we call it shadow map. This shadow map here is rectangular, but for lighting they're typically square. And they have resolutions such as 1024 by 1024 or 2048 by 2048 width and height. Even though 1024 might not seem like it's a large number, when you multiply them together you get something beyond 1 million pixels, or texels in this case. So it's an expensive operation to render the scene from the point of view of light and to generate this kind of shadow maps, just to be able to lay the shadow on your objects for extra realism. So we should watch out where we use such things and only use it where necessary. To explain this algorithm further, considering we already understand how the light views the scene in isometric mode, like that, let's come back into perspective mode and teleport ourselves somewhere to the place how the camera would see it, how the camera would see the scene. So for example, from the point of view of player, we might be somewhere here in the scene, and we might be rendering all of those pixels on our screen, which is several million pixels. It's a pretty large number. And we might be curious that, hey, we're looking at this kind of pixel here, it's having this wooden texture, but what about the shadow? Should it be covered in the shadow, or should it not be covered in the shadow? And we would have to query our own directional light to be able to determine whether to darken it or whether to keep it light and illuminated. So for this fragment, we would teleport back and look from the point of view of light. Is something obstructing this pixel in the shadow map texture, or is it visible to the light? And if it's not obstructed by anything from the point of view of light, we teleport back into our camera and we make it bright. Otherwise, we keep it dark. And we have so many pixels here. We've got several million. This kind of rendering has to happen at least 30 times a second, or preferably 60 frames per second. So there is lots of computations to perform when comparing against such shadow maps. And additionally, these directional lights, and pretty much all the lights in Unity, they have additional settings that you can tweak. So if I select the directional light, the cool setting that we can toggle is the switch between the hard shadows and the soft shadows. The way that the soft shadows are working is when we have some kind of pixel or fragment that we are interested to know whether it's in the shadow or not, instead of just looking at a single little spot in the shadow map, we will look at like a range of pixels around the query point, and we'll average them together. This will result in softer shadows, but for every single point that we are interested in, we have to perform multiple samples, which is of course going to increase the cost and will require more performance to be drawn from your computer. So soft shadows is good, but perhaps consider using hard shadows if necessary. And additional adjustments that can be done lie in the actual settings for this project, which describe how to constrain certain lights, whether you are allowed to have multiple light sources or just a few, and how many lights can contribute to any given object when illuminating it. To adjust such lighting settings and to constrain your performance drain, you go into Edit, Project Settings. The two parts that we're interested in is the graphics and the quality portion. As you can see in the quality, we are given several lists, for example, fastest, beautiful, and fantastic, and the columns represent the devices that we intend to run this on. We could disable certain quality levels entirely by unticking them from here, and this would mean that for iOS, for example, we would only have the fastest version available because all others are disabled for iOS. And the green check marks mean what is the default variant for this platform. You can change the default variant by clicking on this triangle and picking, for example, beautiful. This means that for the iOS, the beautiful will be the default variant of quality settings. As I click between them, you can see that the settings do change because each portion here is tied to its own specific list. So let's look at the fantastic variant. If I click on it, the most important parts are the distance shadow mask and the shadow mask. The distance shadow mask is more expensive than the normal shadow mask because in distance shadow mask mode, both dynamic and static objects, so those that have promised to never move, both of them can cast real-time shadows within the set shadow distance. Beyond this distance, the static objects get shadows from other static objects and not from the dynamic objects. Beyond this distance, static objects get shadows from other static objects from the shadow mask. The more shadows you have, the more performance basically is required from you. So distance shadow mask is more expensive variant. Another important thing to consider is when you have particle systems, for example for smoke or fire or sparks, you might want to reduce the particle raycast budget just so that there is suddenly no huge number of particles on the screen that you wouldn't know about. Like you can set a hard threshold right here. 4000 is plenty, but you can experiment with this setting. And also when you have crowds of different characters that move around and that are animated, that move their arms, bend their feet and deform, you might want to reduce the skin weights to something like 2 bones, for example. This will reduce the fidelity of how the meshes and the 3D geometry deforms around their skeletons, but will increase performance if you have many of characters substantially. In the next video, we'll look at the graphics settings and also real-time lights, which performance constraints they impose, and how to get around them. See you there! Welcome back! In this video, we'll be looking at graphics settings, at the real-time lights, what sort of constraints they impose, and how can we get around them. Another setting that we'll be looking at is the graphics setting, and because the Viking Village is working with the URP, Universal Render Pipeline, the graphics tab has a slot where you can plug in the URP settings, which is an object, and it will be working around the settings specified in this object. So I'm gonna move this to the side, and I'll left click on this asset. You can see that it's located inside of the rendering, the Viking Village Universal object right here. Let's close this window, and with the Viking Village Universal object selected, let's look at its settings, and in particular the settings that it describes for the light sources. So I'm going to increase the width of this window just to make it easier to look at. And the things that we should consider is the lighting portion right here. So the main light is always the directional light. Here we can specify whether we allow it to cast shadows or whether the scene should have no shadows at all. As I untick it, you can see that the screen becomes blue because we are recompiling the shader. This is necessary because URP is only compiling what is necessary at this very moment without dragging any kind of unnecessary code behind. But this is what our scene would look like without the shadows. So the main light is up there in the sky, and the objects that are seeing it now do not cast shadows. They will only shade themselves, depending on whether their surfaces face towards the light or face away from it. But there is no shadow dropped nearby of these objects. This kind of shading is diffuse shading, and it's basically the way to illuminate objects in a proximate way to make them brighter when surfaces face towards the light, and adds a bit more depth. But shadows do play an important role, so for the main light you might want to keep this on. But for the shadow resolution, for the resolution of this grayscale image, the shadow mask, which you have here, this resolution you might want to reduce, which is going to make it contain less texels or less pixels, and it will make it more grainy. And as a result, when we query any kind of pixels around here against this shadow map, we'll see more jagged edges. So if I change the resolution, for example, to 512 by 512, it's going to become really bad. And you can see that the pixelation really starts being visible. So 4K or maybe 2K, as you deem necessary. There is also an option for additional lights. So other light sources like lanterns or campfires or light bulbs that can shine around your scene and add extra depth. You can specify whether you want to allow them to cast shadows or disallow that. And you also have an ability to specify how many objects, how many lights can affect any given pixel. So for instance, if I lock this inspector window and right click on it and open another inspector window right next to it that is not locked, I will then go into the scene, press Ctrl-Shift-N to create a game object. We'll bring it up closer here, and for it I'll attach a light component, make it point, maybe rename it to a point light, and we'll specify that I wish to have hard shadows. Also notice that as I'm doing this, it will be able to cast the shadows because in the additional light settings, I specify that the additional light sources, all the lights that are different to the directional light, they are allowed to cast shadows. So if I do bring this light source closer and maybe make it have more intensity, if I bring it to some darker place, you can see that it does cast shadow. And if I were to have several light sources like this, so maybe let's really crank up the intensity so that you can see it in action. You can see that given any kind of pixel right here, this pixel is considering illumination of 2 light sources at once. And we can go even as high as 3 light sources and have 3 like triple shadows being cast from the single object, because this is what we specified here. We allow up to 3 lights to affect any given object. If we are really tight on the budget, we might go to 1 light or maybe 2. But as we decrease this number, notice that some lights get priority over the pixels, depending on the distance to this light. So use this setting as a hard threshold of the number of lights that you can have in the scene. And you can also specify if you want to impose any kind of shadow constraints or reduced shadow resolution for additional lights by using the shadow resolution for the atlas, decreasing it. This is going to be very little, so you're going to have only one small shadow patch. Or increasing it, but for additional lights, because they're usually close up to the camera and don't have huge range, 1024 can work just fine. Finally, there are 2 different ways of how lights can illuminate objects. You can carry out illumination per pixel or per vertex. And per vertex illumination is going to be more coarse, but it's going to be less expensive, because as the camera is rendering the frame, it will only carry out lighting computations around the vertex points or the coordinates which create the object. So if I zoom up on this rock, and if I, for example, go into a shaded wireframe mode, when I click on the object, and also I have to make sure that the selection wire is enabled, you can see that this object is consisting of several polygons, several vertices. For example, 1 vertex here, 1 vertex here, 1 here. These are the points where the illumination query will happen. So this point will question, am I visible to any kind of light sources, or am I obstructed by some other objects and hidden away from the light source? Am I visible to the main light, or am I hidden away from it? And this kind of query will happen at every single point. And then for the pixels in between of them, simple blending or smoothed interpolation is going to happen. So we're not going to be questioning per every single pixel whether it's facing towards the light. And it's a much less expensive process to carry rather than per pixel illumination. But per pixel is going to give you a more smooth illumination that is very precise. So this is the setting that you can change here. Another thing to consider when you're constrained by the resolution of your shadow map, for example, for such important lights as directional lights, are the shadow cascades. The shadow cascades allow you to take the shadow maps and to subdivide them into several regions. So rather than having one single shadow map, you're going to have basically the same representation of the shadow map. However, it's going to be rendered in small sections. By doing this, we enable several variants of splits that we can explicitly control. Anything within this range is going to be using the most crisp and the nicest portion of the cascade. And anything further away than, for example, 75 meters is going to be in this green region that is going to be using a cascade with less resolution. And finally, all the items in this yellow region are going to be using even smaller cascade. And finally, the last border controls anything beyond that. It's going to get the worst shadow quality. But by doing this kind of prioritization, we're able to grant more shadow quality to those objects that are close to the camera. We prioritize such objects based on their distance. We can also disable the soft shadows altogether for any kind of lights, so that no matter how hard you try to change it on any specific light source, it will not allow you to do that. It will always keep using the hard shadows, even if you try to pick the soft shadows on any kind of light source. In parallel to the lighting, you might also want to consider reducing the anti-aliasing to perhaps 2x. By reducing it, you're going to create images faster, but they will be more grainy, and lines that are on the contrasting regions are not going to appear as smooth. But for mobile devices, 2x is usually enough. It's a post-processing step which happens every time your frame is rendered, which happens 60 times per second. And it just goes through all the pixels and looks at all the neighboring surrounding pixels at their intensities and tries to equalize it using some fancy algorithm. Also, if you are using some kind of post-processing effects that are, for example, screen space reflections that try to reflect environment that is visible in the frame, in the puddles, then you might want to enable, or you probably need to enable the depth texture here. But if you're not using such effects, you can disable the depth texture and save yourself an additional pass that is not required to be drawn by the camera. The directional light has one single shadow map that it applies onto the scene, and as you move the camera, the actual light source, the directional light, it follows you around. So even though the light source appears to be positioned here, as you move around your camera, the light source will move with you and will drag its shadow map in such a way that your camera is always centered within its shadow map. And you can verify this by looking, as you move around, the shadows start to disappear on the corners and start to reappear here. That's basically the effect of the directional light following you around. You can especially see it here. That's because the shadow map of the directional light source is not infinite. It's a constrained image that if you increase it, you're going to use a lot more memory for rendering. And if you do increase it to some large distances, why not to use it on smaller distances, which is going to allow you to use more crisp shadows and increase the resolution on the close-up objects. Therefore, this light source always will follow you around secretly, even though you position it there. However, for light sources such as point lights that we had somewhere around here, these light sources are very expensive because they render 6 shadow maps, much like a cube. So they render an image for the bottom view, one for the upwards direction, and also the 4 sides. Every time you create a light source like this, you have to understand that you're creating additional 8 shadow maps, like a cube map. And the resolution of this light source is very important. If you can, wherever you can, make sure to reduce it to medium, for example, or to have a low resolution of shadow for this light source, if possible. Another type of light is the spotlight, which works very similar to directional light, except that it does not follow your camera around secretly. It will truly stay where it is, no matter where you go. It also renders a square shadow map, whose size is depending on this outer angle. If you really make it wide, the shadow map that it's rendering is going to be stretched for all of this distance, and the shadows will look more coarse. So whenever you can, use the tighter spotlights, if possible, because that will allow your constrained resolution shadow map to be squeezed into a narrower range, resulting in a more crisp shadow. The reason why this thing is circular and not square is because they're applying something called a light cookie. So whenever a pixel arrives and it's curious to know whether it should be illuminated by the light source or not, it will query itself against the shadow map, but also against a circular mask from the point of view of light. And if the point is not hidden by anything according to the shadow map, but falls outside of this mask, then it's just going to be considered as not to be visible to the light and not to be illuminated. This is basically what the cookie is. And you can use a cookie texture for your lights when you have one of them selected. In the emission tab, there is a cookie slot for your texture, which you can plug and have something different than the circular cookie. That's it for this video. In the next one, we'll look at light mapping and how can we freeze light so that we don't compute it at real time and save ourselves a lot of performance. See you in the next video. Welcome back. In this video, we'll look at the light mapping and how can we freeze the lighting to make sure that we save lots of performance during the game and don't have to spend extra resources computing all of this beautiful light at runtime. Real-time lighting alone is not enough, because even though it has ability to give you real-time shadows and ability to move around those light sources, it does not let you to have beautiful illumination, the global illumination. It does not allow you to efficiently simulate light bouncing around the scene. And this bouncing around is the actual most important factor that contributes to the realism of your scene, to the atmosphere of your game. It is how the light interacts with the objects within your game. It's not so much the texture resolution or the vertex count or the polygon count, but rather it is the quality of light that determines how beautiful the game will look like. Consider one of those shader mod packs for Minecraft. It is solidly light, and the way that it reflects off the water and refracts through the glass, that does change Minecraft from being a blocky game to some magnificent, beautiful piece of art. And the real-time light sources can only go so far. So if I pick them and disable them, there is another thing that I want to consider and talk about. It's the light baking. The thing is, you can look at your scene, at the objects in your scene, and you can pre-bake the light into a texture, which is then wrapped around your objects. And as long as your light sources don't move around, like if the sun stays at the same place, then it will be very cheap, because you will not have to perform this computation for every pixel, querying whether it's visible to the shadow map or not visible, whether it should be eliminated by light or not, whether it's in the cookie or outside of the cookie texture. You just wrap around your objects with this nice illumination texture, and it basically freezes the light on top of your objects. Before I begin discussing the settings for light mapping and showing you in more detail, let's close this window because there are two inspectors that we're no longer requiring. This scene, the Viking scene, is actually already unwrapped for the light map and was already light mapped. You can verify this by clicking in this icon and switching from the shaded mode to a baked light map. And here you can see, if you toggle this checkbox, you can see the resolution of light map. The shadows are being baked into the objects, into the creases, and it's basically the lighting that has been baked into the buildings. So any kind of points located somewhere in hidden parts of your scene, they're not able to recognize that there is illumination coming towards them, and naturally these kind of regions are going to be darker than those outside, because those that are outside, when performing this pre-computation, they can see that there is a bright sky above them, that there is a directional light somewhere there illuminating them, and that they are surrounded by lots of bright objects. Whereas portions of the scene that are hidden away from such areas are going to be darker, because wherever they look around, they can just see that there is some dark surface visible to them that isn't really illuminating or contributing to the illumination of such points. And naturally such points will remain dark in the light map. These computations, the sampling for each point, the surrounding regions and surrounding pixels, this kind of computation is very expensive, and naturally we perform it once during editing time to create a texture, and then we allow the player just use this texture without any kind of computations necessary. To create our own light maps, we're gonna go into the window, rendering, lighting, and let me grab this and maybe dock it here next to the inspector panel. I'll increase the size a bit to make it easier to be visible. And as I click on this icon and re-enable the baked light map, we can see that we can adjust the resolution of the light map by going down into here and adjusting the resolution by just dragging left and right or typing in a number. And as you can see, when I'm dragging this, the light map is going to become much more detailed on the objects, because each square on the checker here represents a texel or little fragment on the light map texture that will be generated. The more we have such squares per object, the more crisp the generated lighting is going to be, and more precise and more beautiful, with less artifacts such as these things here in the corners. However, as we do increase the light map resolution, we are also increasing enormously the amount of memory that will be consumed by those light map textures, because the more resolution we give it, the larger the light map textures will be. So perhaps 4 could be a good choice here. It depends on how much memory you wish to consume and how large your game will be. Because textures are the first thing to optimize when you wish to reduce the size of your app. When you are delivering something, for example, to the App Store or Google Play, the size of the app matters significantly, because there is a difference between your app having 200 megabytes or being 7 gigabytes in size, just to download and play it. So this might deter some of the players, and you do want to reduce the size of the light maps as much as you can, as well as reducing the size of other textures. If the scene is fairly large, you will create several light map textures, 5 or possibly even 10 light map textures, in order to wrap every single object that you've specified that should be wrapped in the light map. And this max light map size is only controlling the size of one of such textures. It does not control the total number of textures you can create, because it will create as many as it requires. But you could set it to 4K to make sure that many of your objects are packed into one single texture as much as possible, and that you have few very big textures, if you have, for example, 4K, a few very big textures rather than lots and lots of tiny light map textures applied to your scene. Because typically, the more objects belong into a texture, the less context switches a graphics card has to perform to switch between textures and apply them to the scene. So the less textures you have, the better it is. But also, if they're too large, then you might run out of memory on the GPU. So a 2K right now in 2022 is a good trade-off. Light map compression, you don't really have to bother about it because we're going to compress them explicitly in a moment. But normal quality or high quality is a good start. Light map padding adds gaps between the objects on the light map. So whenever you are baking this light map, it's going to create a texture that will look, if I pick one of the objects, go into the inspector panel, click on it once again, it will look something like this. So this is one of the generated light maps, and you can see that it might look like a mess, but in reality it's describing the lighting on every object visible in the scene. And between them there is a padding, which is only a couple of pixels, so it's not really visible here, but your objects get spaced out. And that's important because if you don't have this kind of spacing between them, then you're gonna have light jumping around from one object to another one, especially if you decide to compress those light maps and to reduce their size. Compression algorithm, it averages out colors into certain regions and makes it look a bit pixelated. The same thing will happen here. If you do not have padding between your objects, when you apply compression, you're going to have some light bleeding, and you might see that this shadow, for example, appears suddenly on this portion of the roof, and you wouldn't know why it appeared there. So back in the lighting section, it is important to have at least 2 pixels between objects. Don't be too greedy, and don't try to increase the resolution of the light map by reducing those gaps. The other settings that we might want to consider that are important are the direct samples, the indirect samples, and the environment samples. The direct samples is the number of queries that every single point will perform when rendering its brightness. So for instance, let me select a suitable point, for instance, somewhere here. So this square might belong to a portion of light map. It might sit somewhere in the light map, and this square might be curious. It's located here in this scene, in this point, in this part of the scene, and this square is interested what is surrounding it. The direct samples are the samples that this particular square will send towards light sources, and we'll see if this ray reaches the light without being intercepted by some other objects that might be covering this portion right here. If we have several light sources, maybe we have like 32 different directional lights, then it will have this budget to query every single light, and it will still work fine. If you do really want to increase the number of direct samples, just put it to something like 60, and it will allow your texel to sample 64 different directions before coming to a conclusion about its intensity. So, for example, if there are lots of creases and different gaps through which the light might shine, maybe 32 will not be enough, because certain samples will be unlucky and will not get through those gaps and through those holes towards the light sources. So consider the setting. The indirect samples is the number of samples that emissive surfaces will send outwards. So, for instance, if you have a glowing wall, then this kind of surface will send rays on the nearby surfaces and will basically send photons that can land on such surfaces. So the surrounding regions should be receiving lots of such photons, and 512 is a good amount because it allows your emissive entities like maybe TV screens or LED screens, billboards and so on that are emissive but which are not lights with the shadow maps. This setting allows such entities to emit photons on the nearby surfaces. And the environment samples is the final setting that we should consider. It is how many samples such a texel will draw towards the skybox. So the skybox typically contributes a lot to the illumination, and it's important that we do send enough samples towards the skybox to make sure that we squeeze ourselves through various gaps that might be on our way towards the skybox. So if there is, for example, a roof with a hole, but I don't think there is in this scene, for example, maybe this texel, there is several objects on the way between this texel and the skybox, like this roof or this beam. So having this budget is an important factor. You might want to have it 512 because you want to give a chance, a big chance for this texel to actually encounter sky several times as it's performing samples. Because the texel is not able to render the scene like this, like a camera. It has only a very constrained budget. So it will not see those this nice resolution of the neighboring environment. It will only see 512 samples, so maybe like, I don't know, 32 by 32 pixel image around itself. So it's pretty blind, but it's sufficient to see what neighboring objects surround this texel to arrive at the conclusion of how bright it should be. There are also different settings that can allow you to tweak your light maps further. The shadow mask is the most expensive one, and it allows to blend shadows from the real-time light sources onto this baked shadow that is baked into the light map texture. The subtractive is the most cheap, and the baked indirect is something in between. The another setting that you can consider is the directional or non-directional light map that you can create. Non-directional light maps add nice shadows and highlights, but they will not allow you to have dynamic specular highlights. So for instance, if you have a glossy metallic surface onto which you have baked this texture, this metallic surface doesn't really remember where the light is relative to this surface. If it's there, then it will not remember it. And if we want to observe a nice highlight on this metallic surface, we'll not be able to perform this computation because the direction of the light source is unknown. If we do want to have those kind of highlights, we should pick directional light map. And it will create these _deer textures, which will double the size of your light maps. But it will allow you to have those nice specular highlights baked into your light map along with the intensities. Finally, once everything has been computed, you might want to look at the filtering of the light map. The filtering option is right here, and you can select none, auto, or advanced. With the advanced option, you can pick which kind of filter you wish to use. Their job is to take the harsh samples that have been generated, take the photons that have been landing on the surfaces, and blur them out and make them interpolated between each other, so that it doesn't look as noisy and as grainy. It just takes in those bright spots and blurs them out in a way that looks more plausible. Keep in mind that light map will only be applied to objects that are marked as static. So if we go into the inspector, and let's click on one of those houses, for example, unless they are ticked as static, they'll not contribute to the light map computation. So you can untick it, and yes, for children, and you can see that the checker has disappeared. This signifies that the object is not considered in the light map, but you can still see that it's using the old light map texture from before, because you can see black and white shading on it. So if you do want to set multiple objects at the same time to be using the light map, you might want to pick their parent game object and tick static. Make sure that contribute GI is ticked on. That's it for this part of the lecture. In the next one, we'll check out one of the most important parts in light mapping, making sure that all the objects have uniform scale in light map, without which your light maps would be way too huge or too unfair towards some objects. And also we'll look at how to compress them. So, see you in the next video. Welcome back. In this lesson we'll look at one very important technique, which comes down to making sure that all of your objects are treating each other fairly before actually hitting the bake button for the light mapping. And also we'll look at how to reduce the size of your game drastically by manually compressing the light maps to a very compact format. Another very important point to consider is that the light map resolution can be tailored per object. So remember how we were adjusting the light map resolution for the entire scene in this lighting window? We were doing this inside of this window using the light map resolution factor. So we were dragging this and we were increasing the resolution for the entire scene. But a very important crucial part of light mapping is to make sure that all the objects in your scene have uniform resolution to begin with. So you could click on one of those objects, for example, on this house, and for this particular house, you could go in and increase the scale of light map to a very large amount. And you can see that the checker really looks fine-tuned on this house. So this means that it's going to be taking a lot larger portion on this texture because it will grab more pixels from this texture at the expense of other objects that also land in this texture. It's very important to make sure that the resolution in your scene is uniform across all the objects. So if you do suddenly notice that there is an object which is using a much coarser version of resolution for the light map, you wish to pick this object and you wish to increase its scale in light map to match that scale of the surrounding objects nearby of it. And if you see something using too much resolution, perhaps even sometimes I've seen it to be something like this, where you look at it and you're like, there is so many checkers on it that it looks like one single uniform color. Those kind of objects are the first things that you should focus on. You should select them and reduce their resolution to be more fair towards all the other objects that are going to be also sampling from the light map. And once you've ensured that your scene and your objects have more or less equal resolution of light map on them, so the checker looks the same on all of the objects, then you can say that they've been treated fairly, and you are able to come back into the lighting and only then increase the light map resolution like this, if you need to. So to conclude, use directional light maps if you do need the specular highlights on your objects, such as metallic surfaces. If you don't care about them, disable directional light maps. It will decrease its size by a factor of 2 and the size of your app. Make sure that all of the objects have fair resolution, and only then play around with the global light map resolution in the light settings. Only increase the size of light map to a certain amount, because if you do increase it to very excessive numbers, you might run out of the GPU RAM, and it might decrease the performance of your game, because textures will have to be unloaded and then reloaded back at the same time to be used. If you have only a few textures, this will cause lots of context switches and will be slowing down your GPU performance. So try to put as many objects as you can into the single texture. And once you're ready, you can click Generate Lighting, which will create light map textures for you to scrub through and to verify. If for some reason you can see that the light map doesn't look nice on certain specific regions, and you just cannot fix it alone by tweaking those settings, you can always take this light map and bring it into Photoshop and paint it manually, or maybe blur some things out. Now, the compression of light maps is the final thing that we'll consider, because light maps do take enormous amounts. This 2048 by 2048 light map takes 5 megabytes, and there are so many of those textures right here. Each one of them is 5 megs at least, and also the directional portion of light map is also 5 megs. So it does increase the app size a lot just for this single scene that you have in your game. And imagine if your game is huge, that would cause these light maps to be contributing a lot. So given a texture, or maybe several textures, I'm gonna press Shift and click on a range of them. You might wish to disable MIP maps on them, which is gonna reduce the size of the textures by a third, but might make it look grainy if they're far away in the distance. But for light maps, usually you could get away with it. So disable generate MIP maps. And in the default settings, tick on the crunch compression and play around with the settings. Sometimes you can get away even with 33% quality and hit apply, which is going to reduce the size down to something like 300 kilobytes per texture, which is a substantial improvement over what we had originally. So about x15 reduction in size. If you are deploying into the iOS, make sure to teleport into it, into here, click override iOS, and make sure that you are using either crunched etc2 or crunched etc. Crunched etc is best for light maps because it only considers 3 channels RGB, and it also imposes a very hard constraint in that your texture has to be a multiple of 2. So either 512, 1024, 2048, and so on. Whereas crunched etc is a more relaxed version of such compression. It only requires that your texture has width and height divisible by 4. So we'll pick RGB crunched etc, reduce the size to something like 30, 32, and hit apply. And one additional bonus thing that you should consider is that the objects that are receiving those light maps, they are using 2 channels. One channel is called UV0 and another channel is called UV1. That second UV channel describes in what sort of way to unfold the 3D geometry of a given object onto a 2-dimensional surface, which is very useful when you want to know where to sample from a texture or from the light map texture. So the second UV channel of your 3D model is going to determine how compact your 3D model is laid out on a 2-dimensional flat surface. And sometimes you might get away with the default settings that Unity allows you to apply to the object, because it can help you to create the second UV unwrap channel automatically. But in many cases it might not be very usable, or it might be not performant at all, compared to having your own artist craft this second UV channel manually for you to make sure that the object is unwrapped very nicely onto a 2-dimensional surface and there are no gaps between parts of this object, and it's very tight. So consider which kind of objects you want to work with. In many cases, complex objects such as, for example, this fence might be not the best choice to be automatically unwrapped by Unity. You might want to do a custom unwrap for such items here. But for large surfaces like these roofs, for instance, it might be good. The trees typically also require such adjustments, the manual creation of the second UV channel. Otherwise, they'll be polluting the light map too much and are not going to be sampling from it efficiently. Just to illustrate the example, let me click on this roof, for instance, or even something that I used to check before, this particular roof right here. And you can see in the mesh renderer component of this roof, because we've already carried out the computation for baking light map, it's already being assigned one of those textures that we saw earlier here. I can double click on it and it will open up the view for this texture. I can use my mouse scroll key or scroller to zoom up, and you can see that portion of this roof have been arranged in a more or less okay way. They are pretty packed together, they're not scattered around. So the second UV channel for this texture is more or less okay. If you had your custom artist, you could instruct him to maybe rearrange those elements to reduce the empty spaces and gaps so that it's more tight and takes less space on the light map and therefore allows other additional objects to be placed nearby instead of just having those empty gaps. But that depends on your desires. Just make sure to select very intricate objects that are obviously not going to be working well with the default Unity's unwrap, and give them to your artist so that they ensure that the UV unwrap is very nice. For example, this is also a good UV2 unwrap because all of the elements of the object are arranged very tightly and nicely with very few gaps. If you were to give Unity instruction to create an unwrap, it will probably create something much more ugly than this automatically. This is looking like a handmade custom second UV channel unwrap done by the artist. The way to create automatic unwraps, by the way, is if you were to click on this roof, click on its mesh filter component and on its mesh, it will bring up this folder. You can see that the roof belongs to this object. It's a 3D model. And when we click on it, we could scroll down and click Generate Lightmap UVs. This will destroy any kind of custom UVs for the second channel you might have, your artist might have created, but it will allow you to create such secondary lightmap UVs if you did not have them. In many cases, they will not be tightly packed like you saw a moment ago, but it could be still more or less okay. You might want to increase the angle error all the way up and area error as well. This will reduce the number of cuts and will reduce the number of chunks that will be created when automatically generating those UVs. And the fewer there is chunks, the better, because you take large surfaces and you don't chop them into different parts and don't introduce ugly seams where lighting will interfere with each other. So the larger the chunks are, the better for you, and these settings will allow you to set this for this specific modal. Make sure to hit apply when you're done and you're good to go. You can also specify the gaps, the pack margin. How closely do you want those chunks to be for this specific modal together? And so this concludes the entire lesson about the lighting and illumination and the optimizations that you can carry out to make sure that your game runs extra smoothly and can reach as many customers as it can. In the next lesson, we'll be looking at another very important optimization technique, the user interface optimization, which does surprisingly contribute a lot to the performance drain. And if you're not careful, your HUD, your HP icons, the various buttons on your screen, they might also take their toll and reduce the performance of your game substantially, perhaps just as much as the illumination and lighting, especially on mobile devices. So, see you in the next lesson.